Hello, welcome to section 1.2, finding limits graphically and numerically. Okay, if you were to sketch the graph of f of x equals x squared minus 4 over x minus 2, there would be a hole at x equals 2y. Well, if you look at this, x squared minus 4 over x minus 2, that's x minus 2 times x plus 2 over x minus 2. And the x minus 2's would divide out. And this would be essentially f of x equals x plus 2. And that's the equation of a line. And that's what we're seeing here. But there's a hole at x equals 2. If you remember from your pre-calculus days, that's because even though x minus 2 divided out, still can't be considered in the domain of the original function. So that's why at x equals 2, see x minus 2, where is that going to be 0? That's where x equals 2. So at 2 we have a hole. And I kind of emphasize that with a little hole. I was drawing this in Microsoft Word. So what happens to the graph at x equals 2? It's not defined. To get an idea of the behavior of the graph near x equals 2, we can examine the values on both sides of 2 as x approaches 2 in table format down here. So if you were to plug these values in, you could put this in your calculator. Under the table format, it's really a good way to do things. If you put in 1.5, in fact, why don't I show you how to do that with the calculator. So I'm going to be using the graphing calculator, the TI-89. So here's my TI-89 calculator. Trying to get out of the glare of the lights. I don't know if I even need the lights there. Okay. So if I look at y equals, I'm going to go ahead and put my calculator in function mode. And the equation was, or the formula was, x squared minus 4, so parentheses x squared minus 4 divided by x minus 2. Now I can go over to the table format. If I go to table set, first of all, notice that it says here ask. It's flashing ask. That means I'm going to input the values. So I go over to F5, and here we go. The values, you remember from your notes, and you can look those up, and I'll get that back on here in a second. We start off 1.5, then I'm going to 1.75, and I'm going to, the next is 1.9, and then 1.99, and then 1.999, and then the next one at 2, it says undefined. And you go on the other side of this, 2.5, 2.25, 2.1, 2.01, 2.001. And we can see the behavior. What are these values going to be? So I'm going to go back to the graph now. I'll go back to our notes, I should say. If I start filling these values in, 1.5 we said was 3.5. 1.75 is 3.75. 1.9 is 3.9. 1.99, 3.99. 1.999 is 3.999. But at 2, it's undefined. Come the other direction. 2.5 is 4.5. 2.25, 4.45. 2.1, 4.1. 2.01, 4.01. 2.001, 4.001. So where's it going? I'm not asking for the exact value at 2, but what is the behavior as we're approaching 2? As x is getting close to 2 on both sides of 2, f of x gets close to 4. So we write this in what we call limit notation. So I'm going to raise this up here. We're going to see limit notation. limit notation. Limit as x approaches 2 from either side of f of x is 4. So this graph is going towards 4. Going towards 4. So if f becomes arbitrarily close to a single number L as x approaches c from either side, not either sides, the limit of f of x as x approaches c is, limit as x approaches c of f of x equals L. So let's look at this first example. Here it's complete the table and use the results to estimate the limit. Use a graphing utility to graph the function and confirm your results. So we have limit as x approaches 2 of x minus 2 over x squared minus 4. Okay, so for 1.9 we have 0.25641, 1.99, 0.25063, 1.999, 0.25006. So it looks like from this direction they're going towards 0.25. How about 0.21, 0.2439, 2.01, 0.24938, 2.0001, it's 0.24999. So from either side, this is their key place right here, it's going towards 0.25. So our limit as x approaches 2 of x minus 2 over x squared minus 4 is going to be 0.25. We can graph that as well. Would you like to see that graphed? I need to erase the board, so if you want to save any notes anytime, if you want to be able to write this stuff down, you can always click pause. No, I just pretend to be paused. You can click pause, and then you can write stuff down and then hit play again. So I'm going to erase, so click pause now, and I'm going to erase. So if we want to see this graphed, this is x minus 2 over x squared minus 4. Okay, I'm going -5 to 5, my x's and y's. So as we're approaching 2, right there, let me make this a little bit bigger. I really want to focus on what's happening right here. This is all the way up to 1 there. So where's that going to be? We can use our calculators here at f of 5. And actually, I don't think we need that. We can just do some tracing. Trace. Oh, F3 traces it. Okay. So here we are tracing it. I'm looking at these y values. So here we're getting closer and closer to 2. Oh, we just crossed over. So 2.08, we're at 0.244. At 1.96, we're at 0.25, so it kind of shows you what's happening right there. But if I go to F5 and then have it give me the value, if I type in 2, it'll just be blank because there's actually a hole. Even though this graph doesn't draw the hole, there is a hole there. And it really can't show the hole because it's infinitely small. It goes close on either side. Okay, let me go back to our notes. Okay, find the limit of f of x as x approaches 1, where f is defined as 2 when x is not 1, but it's 0 everywhere else. So at 1, the graph is down here. Everywhere else, it's 2, and there's a hole down to there. So what's our limit, though? I'm not asking for the defined value at 1. What is our limits as x approaches 1? As x is going to 1 from either side, what's the behavior of this graph? Well, only place it's at 0 is at 1. But as we get close to it, we could be at 1.000001 or 0.9999999, and on either side we're going to be at 2. So our limit is 2. And so we're not talking what is the defined value there, we're talking about what is the behavior of the graph as we get close to there. So that's saying the limit as x approaches 1 of f of x is 2, while f of 1 is just going to be 0. Okay, let's go to example 3. Show that the limit does not exist for the limit as x approaches 0 of the absolute value of x over x. So the absolute value of x is defined to be x when x is positive or equal to 0, and it's defined to be the opposite of x for x being less than 0. So let's look at the definition for the absolute value of x over x. That's going to be x over x, which is 1 for x being greater than 0. Notice I don't include the 0 now because I make it undefined. And that would be equal to the negative of x over x, which is negative 1 for x being less than 0. So here's our graph. As we're approaching 0 from the right, it's going towards 1. As we approach 0 from the left, it's going towards negative 1. So the limit as x goes to 0 of the absolute value of x over x does not exist. Because going from the left or on the right, it's not going to the same place. For the next one, discuss the existence of the limit as x goes to infinity of 1 over x, as x goes to 0 of 1 over absolute value of x. This graph would look like the following. So as we go towards 0, it's going to infinity in either direction. So the limit as x goes to 0 of 1 over the absolute value of x, that's going to be infinity. Now, infinity is not a defined value. So the limit as x goes to 0 of 1 over the absolute value of x does not exist. Can you go on to the next page? Feel free to pause if you'd like. Find the limit as x goes to 0 of cosine of 1 over x. So let's do a little table here. Let's try 1 over pi. Then we'll do 1 over 2 pi. And then we'll do, then we'll do 2 over pi. And then we'll do 3 over pi. Then we'll do 4 over pi. And then we'll do 5 over pi. And then we'll do 6 over pi. So cosine of 1 over pi is negative 1. Cosine of 2 over pi is going to be 0. Cosine of 3 over pi is 0.5. 4 over pi is going to be 0.7071. 5 over pi, 0.809. 6 over pi, 0.866. If we want to go closer to 0, though, I mean, here we're seeing going closer to 0. What if we did 1 over 2 pi? That's 1. 1 over 3 pi, that's negative 1. 1 over 4 pi, that's going to be 1 again. So as we get closer and closer to 0, the graph is looking something like this. Comes over here and then jumps like that. So that the limit as x goes to 0 of cosine of 1 over x does not exist. Okay, common types of behavior associated with non-existence of a limit. F of x approaches a different number from the right side of C as it approaches from the left side. F of x increases or decreases without bound, goes up to infinity. Or F of x oscillates, like we saw here, between two fixed values. It's going between negative 1 and 1 as x approaches C. Definition of limit: let f be a function defined on an open interval containing C except possibly at C. And let L be a real number. The statement the limit as x approaches C of f of x equals L means that for each epsilon greater than 0, there exists a delta greater than 0 such that if 0 is less than absolute value of x minus C less than delta, then the absolute value of f of x minus L is less than epsilon. Now let me be quite candid here. This here is not going to be a recurring thing in the class. You'll see it once or twice, but it's really not the basis of it. What it's saying is we can pick one interval small such that the other interval is small as well. That's really what it's saying, and we can find a relationship between them. So people get really stressed and just focused on this part. It is about the definition of limits, but it's not going to be the basis of this class, so please do not let this part frighten you. Okay, epsilon's called that's epsilon and that's delta. So we have an example here where I'll work through one. There might be one of these in the homework, but it's not every problem in the homework. Find the limit, then find delta, which is positive, such that f of x, absolute value of f of x minus L, is less than 0.1 when 0 is less than absolute value of x minus C less than delta. And I forgot to type this in here. We have f of x equals 4 minus x over 2. And the limit as x goes to 4 of 4 minus x over 2 is going to be 4 minus 4 over 2. So here x is 4. 4 minus 4 over 2, which is 4 minus 2, which is 2, and that's going to be our L. So we want to find the absolute value of f of x minus L be less than our epsilon, where our epsilon was defined to be 0.01. So the absolute value of 4 minus x over 2, this is my f of x, minus the limit, that's 2, needs to be less than 0.01. So 4 minus 2 is 2, so 2 minus x over 2 is less than 0.01. I can factor out a 1/2, so 1/2 times the absolute value of 4 minus x is less than 0.01. So we could say 1/2 times the absolute value of -1 times 4, x minus 4 is less than 0.01. So 1/2 times the absolute value of -1 times the absolute value of x minus 4 is less than 0.01. Absolute value of a -1 is just 1, so we can drop that out. So it's 1/2 times the absolute value of x minus 4 is less than 0.01. Solving for this, the absolute value of x minus 4 is less than 0.02. So that for epsilon being 0.01, delta is 0.02. So our epsilon was 0.01, so delta is 0.02. Delta being 0.02 makes this line up perfectly here because our C is 4. Okay, let's go on to the next page. Feel free to pause if you need to pause that. Okay, find the limit, then use the epsilon-delta definition to prove that the limit is L. So here I forgot to type this in again. We're going to be doing absolute value of f of x minus L is less than epsilon when 0 is less than the absolute value of x minus C is less than delta. Our f of x here is going to be x plus 3 and the C equals 2. So the limit as x approaches 2 of x plus 3 is going to be 2 plus 3, which is 5, and that'll be our L. So the absolute value of x plus 3 minus 5, this is this part here, is less than epsilon when 0 is less than the absolute value of x minus 2. Because our C is 2, is less than delta. So the absolute value of x minus 2 is less than epsilon when 0 is less than the absolute value of x minus 2, less than delta. Now, our choice of delta depends on epsilon. We need to establish a connection between the absolute values here and there. So the absolute value of x plus 3 minus 5 becomes absolute value of x minus 2. Over here we have an absolute value of x minus 2 as well. So we can choose that delta equals our epsilon. So if epsilon is 1, delta is 1, and so on. But we have an established relationship. We can make this look just like that, as long as epsilon equals delta. Okay, we have one more problem from this section, so feel free to pause if you need some time. And again, I'm spending a lot of time on the epsilon delta. I'm going to the purest math part of this for calculus to really kind of build this up. But do not think that this is the basis of the course. Do not stress about this. Really not something to worry about. I'm showing this to you, giving you some exposure. Okay? Please don't run from the class because you saw an epsilon delta. Okay, example 8. So let's find the limit. Limit as x approaches negative 3 of x squared plus 3x, then use epsilon delta to prove that the limit is L. So our f of x, in this case, is x squared plus 3x. So the limit as x approaches negative 3 of x squared minus 3x is going to be negative 3 squared minus 3 times negative 3, which is going to be, or that's a plus here. That's going to be 9 plus negative 9, which is 0. And that's our L. C equals negative 3. So again, we're looking at the absolute value of f of x minus L is less than epsilon. 0 is less than absolute value of x minus C. It's less than delta. So we have x squared plus 3x. This is our f of x. Minus 0, this is the limit. Needs to be, that's going to be equal to the absolute value of x squared plus 3x. That's going to be the absolute value of x times x plus 3. And that's going to be the absolute value of x times the absolute value of x plus 3. Now this part, it's going to look like our delta part, because that's going to be the absolute value of x minus c, absolute value of x minus negative 3, which is absolute value of x plus 3. So this is the epsilon portion. Now for the delta portion. 0 is less than the absolute value of x minus negative 3, less than delta. So 0 is less than absolute value of x plus 3, less than delta. And since c equals negative 3, choose an interval around negative 3, like negative 4 to negative 2. So if we look at the absolute value of x on the interval, what is the maximum value? Of the absolute value of x on the interval. What's the biggest is going to be? Well, if you put in negative 4, absolute value of negative 4 is 4. So let our delta be epsilon over 4. So if we have the absolute value of x plus 3 is less than delta, then the absolute value of x times the absolute value of x plus 3 is less than delta times 4. Bringing this in, absolute value of x times x plus 3 is less than epsilon over 4 times 4. So our delta is epsilon over 4. We can choose it that way. And then the absolute value of x squared plus 3x is less than epsilon. So what we're seeing here then is that there is a connection between our delta and epsilon parts. And by saying the absolute value of x here and 4, we will know 4 is bigger than or equal to x on the interval. That's why we could bring that in. And we chose delta to be epsilon over 4 so that it would cancel and give us an epsilon in the end. So that's epsilon delta. I know that's kind of frightening for this second lesson in the calculus class, but there you go. I do know that some people don't even cover this. I think it's good to have the exposure to it to see, hey, this epsilon delta thing. So take a look at that. Very little of the homework is associated with this, but it's here. So do your homework and send me your questions. Thank you.